Let's be real, crypto can sound overwhelming. You hear terms like blockchain, miners, wallets, seed phrases, smart contracts, and it feels like a whole new language. In this video, I'm going to break it down step by step so you can finally see how all the pieces in the crypto puzzle connect. So it all starts with blockchain. What even is it? At its core, a blockchain is just a digital record book. Imagine a notebook where you write down every transaction. Once written, no one can erase it. And instead of one person keeping the notebook, thousands of computers around the world keep identical copies. So it is impossible to tamper or change, or in other words, it's immutable. Every chain has to start somewhere. In blockchain, it begins with block 0, the very first block. Any information or transactions that need to be stored are grouped together into a page, which we call a block. Once that page is full, the network of computers checks and agrees that everything on it is correct. Only after this verification is the block locked in, which is what makes blockchain secure. No single person controls it. Since block 0 has no preceding block, it stands alone. Every block created after that not only stores new transactions but also keeps a reference to the previous block. This linking forms a continuous chain of blocks, hence a blockchain. Now, the biggest use case for blockchain so far has been cryptocurrency. Digital money like Bitcoin and Ethereum won't exist without it. But the idea goes way beyond money. People are already using blockchain for supply chains, property records, even digital art. Still, for now, let's stick to Bitcoin because that's where the story really begins. Back in 2009, someone or some group named Satoshi Nakamoto launched Bitcoin. By the way, Satoshi's identity still remains a mystery to date. The very first page of this digital ledger was called the Genesis block or block 0. This block wasn't just symbolic, it actually contained 50 Bitcoin as a reward for the miner who created it. But here's a quirky detail. The coins from this first block were unspendable. They can't be moved. Satoshi also embedded a coded message in the Genesis block.
The Times, 3rd January 2009. Chancellor on brink of second bailout for banks.
This wasn't just a random headline. It served as both a timestamp and a statement of intent for the purpose and future of Bitcoin. The message references a major financial event, the UK government's second bank bailout during the 2008-2009 financial crisis. By including it, Satoshi highlighted the problem Bitcoin was designed to solve: reliance on centralized banks and governments. In a way, the Genesis block itself became a historic marker linking the birth of digital money to a real-world economic event. So what's in a Bitcoin block? Think of it like a page in a ledger or notebook. Each block contains two key components. The block header, that's like the cover page. It includes metadata such as the timestamp, the difficulty target, and the nonce. Most importantly, it contains a reference to the previous block's hash, which is what links the entire blockchain together. And second, the transaction, the actual contents of the block. These are of two types. First, the coin-based transaction, the first and special one, which rewards the miner with new Bitcoin and collects all transaction fees. And second, regular transactions, payments and transfers between various users. All of this together ensures that each block is unique and securely connected to the chain. Change even one transaction and the fingerprints no longer match, breaking the chain. We will go through these in detail, but before that, we need to take a detour to understand hashing. A hash function is like a machine that takes any input, text, numbers, or even a whole block of data and turns it into a fixed length code, which we call a hash. No matter how big or small the input is, the output is always the same length. Here's a simple example. Let's take two inputs and put it through the hash function. Notice what happens? Just changing the capital H to lowercase completely changes the hash. Hashes are extremely sensitive. Even tiny changes create a completely different output. So whether you put in a single character or an entire book, the hash function will always produce a fixed length, unique output. That means no two inputs will ever produce the same hash. In blockchain, this is crucial. Each block's hash acts like a fingerprint for its contents. If even one transaction changes, the hash changes completely, instantly alerting the network that something was tampered with. Another key point, a hash function is a one-way function. It's easy to calculate the hash from the input, but practically impossible to reverse it, meaning to figure out the input just from the hash. The only way to reverse it is brute force, trying every possible input until you find one that matches the output, which is computationally impractical. So which hash does Bitcoin actually use? Bitcoin uses a function called SHA-256, Secure Hash Algorithm 256-bit. It takes any input, like a block of transaction, and produces a 256-bit output, which is a long string of letters and numbers. That's the fingerprint for the block. Now, why is it basically impossible for two different inputs to produce the same output? This is called a collision, and SHA-256 is designed to make collisions astronomically unlikely. To give you a sense of scale, SHA-256 can generate roughly 2 raised to the power 256 possible hashes. That's so many that it's estimated to be more than the number of atoms in the entire observable universe. In other words, the odds of two different inputs ever producing the same hash are unimaginably tiny. This is why SHA-256 is considered collision resistant. Every block and transaction gets a truly unique fingerprint. If even a single character changes, the hash jumps to a completely different value, keeping the blockchain secure and tamper-proof. So now that we understand hashing, let's come back to the Bitcoin block and let's zoom in on what's actually inside a Bitcoin block. So as discussed, a Bitcoin block has two main parts. Part 1, the block header. Think of this as the cover page. It's tiny, just 80 bytes, but it carries the most crucial information. First, version tells the network what rules this block follows. Over time, Bitcoin's rules evolve, and this field makes sure everyone's on the same page. Next, previous block hash, the link that connects this block to the one before it, forming the chain. Merkle root, a single fingerprint summarizing every transaction in this block. You can read about this offline, but just imagine all the transactions that are to be put in this block are put through a hash function to get one unique string, that is Merkle root. Timestamp, when the block was mined. Difficulty target, how hard this block was to mine. Nonce, the magic number miners keep changing until the block's hash fits that difficulty target. I will explain the last two in a little bit more detail later. The block body. This is the big section, the actual list of transactions included in the block. At the very top sits something special, the Coinbase transaction. This one's different because it has no inputs. It creates brand new Bitcoin, which is called the block reward. It collects all the transaction fees from this block. Plus, as a bonus, miners can add little bits of extra data here, like a signature or even a hidden message. That's how Satoshi left the newspaper headline in the Genesis block. After the Coinbase comes all the regular user transactions, people sending Bitcoins to each other. Okay, so we know blocks hold transactions, but who decides which transactions make it in? That's where the mempool comes in. Think of the mempool like a waiting room. Whenever you do a Bitcoin transaction, like sending Bitcoin from person A to B, it first goes to this waiting area on the network. Every node keeps its own mempool, storing all the unconfirmed transactions it knows about. Now, miners are like chefs in a busy kitchen. They are preparing the next block, but they can't fit every order on one plate. So what do? They pick and choose transactions from the mempool, and here's the catch. Transactions with higher fees go first. Just like tipping a waiter gets your faster service. Paying a higher transaction fee pushes your transaction to the top of the line. If the block still has room after the high fee ones, miners will include lower fee transactions. So in simple terms, you broadcast a transaction, it enters the mempool, miners grab from the mempool, prioritizing by fees. Once a miner finds a valid block, those transactions are sealed in forever. And that's how your transaction moves from pending to confirmed. So now we are ready to create block 1 to connect to our Genesis block. Now to be more accurate, a Bitcoin block is not created but rather found. Here is how it happens. A miner will create a candidate Bitcoin block, which contains the block header and the transactions. The miner will put the block header through a hash function, and if the hash function output meets the difficulty target, the block is accepted and added to the chain. If not, a new candidate block is created and the whole process is repeated again till a valid block is found. Here we need to learn a little bit more about difficulty and nonce that we skipped before. First, why is difficulty even required? The Bitcoin rules say that each block should be found approximately every 10 minutes. So if we have too many miners mining and finding blocks too quickly, the system adjusts the difficulty to bring the average back to 10 minutes by making the blocks difficult to find and vice versa. So how is this done? The network sets a rule called difficulty, which basically says your block's hash has to start with a certain number of zeros. Here's an easy way to picture it. Imagine you are rolling a 100-sided dice. If the rule says your roll must be less than 10, you've got a 10% chance of success. That's not too bad. You'll probably get it in a few tries. But if the rule says your roll must be less than 1, now you only succeed 1 out of 100 times. Way harder, and it'll take much longer. That's what Bitcoin does. It adjusts this target number up or down every 2016 blocks, which is about 2 weeks, so that on average, one block is mined every 10 minutes. And remember, all this is made possible by the hash function, because there is no way to predict what output it will give. So it's like literally throwing a dice every time, but in reality, it's probably like a 1,000,000-sided dice and you have to roll a 1. That is why mining is so computationally intensive. So now you rolled the dice and it didn't come up 1. So now we have to create a new block. How is this done? First, we change the nonce. Nonce means number only used once. Miners keep plugging in different nonce values, hashing the block again and again, billions of times per second, hoping the result lands under the target difficulty. Most attempts fail, but eventually one miner finds that lucky nonce where the block hash is small enough. At that moment, the puzzle is solved. The block is valid and the miner gets to broadcast it to the whole network, along with earning the block reward. Just a little known fact. If a miner tries every possible nonce value and still can't find a valid hash, they can change other variables like the order of transactions or the transactions themselves, because changing anything in the block body will also change the hash. This creates a new set of possible hashes and gives them another shot at solving the puzzle. So what we have been talking about, all this hashing, guessing nonces, and racing to find the next block, this whole system is called Proof of Work or POW. In Proof of Work, miners compete using computing power. The first one to solve the puzzle proves they did the work and earns the right to add the block to the chain. It's extremely secure, but as you might have imagined, it also consumes a lot of energy and requires specialized hardware. Now, not all blockchains work this way. For example, Ethereum, which used to run on Proof of Work, switched to something called Proof of Stake in 2022. In Proof of Stake, there's no mining race. Instead, people lock up or stake some of their coins and the network randomly selects one of them to validate the next block. The bigger your stake, the higher your chances of being chosen. Kind of like buying more raffle tickets. So the key difference is simple. POW, you compete with computing power. In POS, you compete with capital stake. Both methods keep the network secure, but POS is far more energy efficient since it doesn't rely on millions of machines constantly crunching hashes. Bitcoin, however, continues to use proof of work because it's battle tested, proven, and remains the most secure consensus mechanism ever built. The foundation of why Bitcoin still works flawlessly after more than a decade. So basically, that's how mining works. Eventually, one lucky miner finds the winning block and claims the reward, the Coinbase transaction plus all the transaction fees from the block. And then the cycle starts all over again. Remember, this is a race. Hundreds of thousands of machines are competing at the same time, all trying to be the first to solve the puzzle and add the next block to the chain. It's fast, it's competitive, and it's what keeps Bitcoin secure and moving forward, block by block. What is Bitcoin halving? Every 210,000 blocks, which is roughly every 4 years, the block reward is cut in half. This is called halving. It's designed to gradually reduce the supply of new Bitcoin, making it more scarce over time. For example, the original reward was 50 Bitcoin per block. After the first halving, it dropped to 25 Bitcoin, then 12.5, and so on. Halvings keep happening until the maximum supply of 21 million Bitcoin is reached, which, as per the current parameters, should happen in the year 2140. The current fee at the time of finding a block is 3.125, which at current approximate Bitcoin value of $110,000 is $350,000. Typically, the average number of transactions in a Bitcoin block ranges from 2 to 4,000, and the average cost per transaction, which fluctuates but is currently less than $1. This means that the total transaction fees in a block are typically a few $1,000s, a small amount compared to the block reward itself. Also, you might have thought, what happens once all the Bitcoins are mined? Then the mining rewards go to zero, but new blocks can still be created and the miners will only earn the transaction fees, but there will be no Coinbase transaction.